Hello, my name is Kevin Yu. The date is March 27th, 2024, and this is my 2EI4 Project 3 video report.
This is my circuit schematic for the amplifier. For the transistor, I used a BJT over a MOSFET because BJTs have a higher GM value, which has a better linearity and better performance than a MOSFET. It also offers a lower input impedance, which allows signals to pass through easily. And then for the amplifier topology, I used the common collector topology. This is because it cannot be a common base since Rn cannot be small, and common collector gain is close to 1, which is exactly the description of this project, where gain should be bigger than 0.9, or equal to. Also, having a smaller Rout is an important factor because the gain should be close to 1 as well, as shown in this formula for gain. Now for the calculations, I had defined the GM value, the Rn value, and for our components, I defined R1 and R2 in this schematic. So this one and this one, as well as finding the capacitor components as well. And then these are given. So let's start off with finding GM. So using this equation, 0.2 times VT times 1 plus GM, 1 plus GM times RL is greater than 0.5, which is our VN. At room temperature, VT is 25 millivolts, and RL is given as 100 ohms, as shown here. So basically, I just had to solve for GM, and it turns out that GM is bigger or equal to 990 millisiemens. Next, I had to find input resistance using this gain equation, and it also has to be bigger than 0.9. So since we know GM and we know RL, I also solve for Rn as well. And it turns out that Rn is greater or equal to 1000 ohms. So Rn is also R1, R2, and Rn prime in parallel. So we're looking for R2 and R1, and we can solve for Rn prime using this equation, R pi times 1 plus GM times RL. And R pi is basically Rs over GM, and these are all given. So I also solve for Rn prime, which is around 10,101 ohms. So I basically chose R1 and R2 based on what I have in my kit. And as long as Rn is bigger than 1K ohms, then it's fine. So 10K in parallel with 10K in parallel with 10,101 ohms is 3,344 ohms, which is greater than 1,000 ohms. And that meets the constraint. So these resistances are fine. And then for capacitance, you cannot really calculate them because all they do is basically set the shape of your waveform. And a higher capacitance makes that shape more clear. So I just chose what I had left in my kit. I chose C1 is 100 microfarads and C2 is 10 microfarads. So this is the circuit schematic of the amplifier. So to start off, I have an input voltage of a sine wave that is 0.5 volts with a frequency of 20,000 hertz. And this goes into Rs, which is 100 ohms, and goes through this capacitor as well, which is 100 microfarads. And then it goes into the resistor bias junction. So R1 is 10K ohms as calculated before, and it shares a common voltage with the collector. And then R2 is also 10K ohms, which goes to ground. So the transistor model I used was 2N3904. And Vout is over here, where there's a capacitor of 10 microfarads. And this is our load resistance, which is 100 ohms going to ground. So next, the settings I used for stimulation, I did a transient analysis here with a stop time of 0.0002 seconds. So now let's find the gain of this circuit. So the voltage gain is, the formula for it is V out over V in. So we have V out over here as a sine wave, and then we have V in, which is a 0.5 volt sine wave as well. And as you can see, V out is a little bit smaller than V in. And to calculate gain, let's first use cursors. So V out, as shown here, is 479 millivolts. Let's put that into the calculator. 479. And then you divide that by our voltage input, which at the same X value is around 499 millivolts. Our gain is now calculated to be 0.96, which meets the requirement of gain being bigger than bigger or equal to 0.9. Another thing we could calculate is the input resistance. So as we know, the resistance is the input voltage divided by the current. So let's run this simulation again. So we have input resistance or input voltage of 0.5. I'm gonna reset this. So our input voltage is 0.5 volts, a sine wave. And the current would just be like this, current through RS. And we do the same thing again, where we take cursors, we find the voltage first. So at any given point, the voltage would be, at this point, would be 499 millivolts. And then the current will be around 114 microamps. And to find the input resistance, it would just be 0.49 volts divided by 0.000114 amps, which gives us a resistance of 4,377 ohms. And based off the requirement that we calculated, which Rn has to be bigger than 1,000 ohms, this satisfies this requirement.
Okay, so this is the physical circuit of the amplifier. So let's start off with V in. So V in is going to be this yellow wire, which is connected to the wave gen. The wave gen will input a sine wave that is 0.5 volts, no offset, and has a frequency of 20 kilohertz. So as I can show here, there we go. And then next, I will have a voltmeter 1, channel 1, to look at the input voltage. Next, it will go into RS, which is 100 ohms, going through the capacitor, which is 100 microfarads. And then this is the resistor bias junction here. So we have R1, which is 10k ohms. This is 10k ohms going into a 5 volt DC power supply, which the collector is also connected to. So this is going to be a common collector circuit. And the R2 is going to ground, also 10k ohms. The transistor used is a 2N3904, and the emitter goes in, and then this is the emitter, and this is RL, which is 100 ohms connected to ground again. And then channel 2 is connected to the out, which is right after the capacitor where the emitter is. Okay, now I'm going to test my physical circuit. So to start off, I have my wave gen set at
500 millivolts sine wave with a frequency of 20 kilohertz. I also have the 5-volt DC supply, and this is my scope. So I'm going to run this. And as you can see here, I have channel 1, which is the input voltage, and then I have channel 2, which is the out. So some measurements I took here are the peak-to-peak values, the maximum values, and I also want to check if the frequency is the same. And also, this M1 channel is basically V out over V in, which is the gain. And as you can see here, when I run it, the gain is always around 0.9 volts. So that also checks out. And then, yeah, if I just do maximum of, if I do the C2 over C1, I will get a gain of around 0.9. So let's just do that real quick to check. As you can see here, it's around 0.9. Now for the mid-band gain, what I'm going to do is I'm going to set the amplitude to be smaller values. So let's do like 250 millivolts, which is around half of the amplitude, and see how it affects the gain. So I'm going to do a run. And as you can see here, the gain is still around 9. But if you really wanted to calculate it, or 0.9, sorry. But if you really wanted to calculate it, you take the maximums and then you divide them, and then you see that the gain is around 0.9, right? And I could do that for multiple values. Let's do one more time just to be sure. We could do 100. So 1/5 of the amplitude. And look at the gain again. You notice how the frequency is still the same. Let's just do 91. This ratio, so it wouldn't matter. So yeah, it's above 0.9. So to check linearity, I use the spectrum. And as you can see here, I set my amplitude back to 0.5 volts with a frequency of 20 kilohertz. And as you can see here, we get a lot of noise when we run it. And when we zoom in, we see that the signal strength for both the input voltage and the output voltage are similar, which proves that it's linear.